Hey guys, in this video we're going to talk about specific heat or specific heat capacity. This goes with Objective 5 for Unit 2. And we're going to get out our handy Cornell paper now. Here we go. Make sure you fill in your name, the class period, and the date right here. And the objective that we'll be talking about is Objective 5 in Unit 2. And that has to do with specific heat. And let's get our essential question out. How do I use specific heat to understand and calculate changes in energy? So in our Unit 2 so far, we've been talking about all things energy and particles and what the particles do differently and what effect that has. And so specific heat is just another one of those things that we use to think more about the information. So let's go ahead and define specific heat. It is the amount of energy that is required to raise the temperature of 1 gram of something by 1 degree Celsius. So if we have a value, if you have a higher specific heat, that means that it takes more energy to raise the temperature. C is the letter that we use for specific heat, and it is measured in joules per gram degree Celsius. I'll write that down here in a second. But the higher specific heat that you have, that means that the harder it is to change the temperature. So a higher specific heat is something known as an insulator. That means that the temperature doesn't change very much. This is why you use hot pads to take hot things out of the oven instead of your hands. Your hands, they change a little faster and it burns. So if it has a lower specific heat, this is something called a conductor. The reason metal pans that you use to cook with are made of metal is because metal is a good conductor, and so it transfers that energy straight to your food to help cook it. So insulator, conductor. So C is for specific heat, and it is measured in joules per gram degree Celsius. You can use Kelvin and Celsius interchangeably because the increments are the same, but you got to make sure you have grams and you got to make sure you have joules. So specific heat is a pretty useful thing. Let's think about where it comes from. Remember in one of the objectives we made a cooling curve where we watched the temperature change and then it went flat and then it changed and then it went flat and then it changed. And the interesting thing about this, so this is your temperature here on this side, and this would be, if we look at energy instead of time in joules, joules per gram degree Celsius, what we end up having here is the slope of this line is related to the specific heat of the object. So at different phases it's going to have a different specific heat, and then the amount of energy it takes to do the phase change is called a heat of vaporization or heat of formation, which the honor students, you guys will need to understand that, I think, but not the regular kids. But if you have a substance that has a higher specific heat, I'm gonna get rid of this. Can I get rid of that? Nope, I can't get rid of that. If you have a substance with a higher specific heat, it will have a steeper slope, which you don't even have to know that. Okay, so let's move on. We're going to talk about some calculations here. So I'm going to go to, there it is. So we'll do some calculations here. So remember, since specific heat is the amount of energy that is needed to raise 1 gram of something by 1 degree Celsius, and that unit is joules per gram degree Celsius, we could actually use that to come up with the equation. So the amount of energy that it takes, we give the letter Q, and that's going to be measured in joules. So this is our heat that is added or taken away as joules, and then we've got to get joules over here by itself, we'll have that specific heat, which I'm going to write specific heat. Specific heat and specific heat capacity are two words for the same thing. You can use them interchangeably. We have, we'll be multiplying here, right, to get the grams and the degrees Celsius over there, so we'll be multiplying by mass. and that'll be in grams. This will be joules per gram degree Celsius. And then we'll be multiplying that by the degree Celsius, which is going to be the change in temperature. Change, and you got to make sure you type in the change in, because we don't really care about the before temperature or the after temperature. We want to know the change in temperature. And degrees Celsius or Kelvin would be okay. Okay. So the way I remember this is that Q equals country music television. That's a good way for it to be stuck in my head. Country music television is hot is a fun way to think about it. That was how I actually learned that equation when I was in high school. So when you use this equation, what you end up having are some questions that you have to answer. So let's get an example question ready to write down. So here's our first example. How much energy must be removed to lower the temperature of 500 grams of water from 35 degrees Celsius to 25 degrees Celsius? Now, in order to be able to answer this question, there's one piece of information that it doesn't say here. This will often be something that is given to you, but the specific heat of water is a very constant value. In fact, you can use specific heat to identify different materials. For water, it is 4.184 joules per gram degree Celsius. So that is the other thing that we need to have here. So we're going to use that equation. Remember, Q equals CM triangle T. Now this is just like a Mad Lib. So we're gonna put numbers in here. Q, C, M, and T. But those boxes may not be big enough. We'll have to see. Okay, so how much energy is code for Q? So Q is what I'm looking for there. If I keep reading the question, I can get some more information. How much energy must be removed to lower the temperature of 500 grams of water? That is my mass. So I'm going to put the 500 right there. And then the next thing I need is well, it says from 35 to 25 degrees Celsius. That's my change in temperature, but neither of those numbers goes in there. So let's think about it. It was 35 and now it's 25. That's a change of 10 degrees Celsius. And to signify that it went down, I stick a negative in there. So I'm going to put a negative 10 degrees Celsius right there. And then the only other piece of information that I need is that the specific heat, which I have right here, and that's the 4.184 joules per gram degree Celsius. So I don't have a lot of units right here, but that's joules per gram degree Celsius. I got the degrees Celsius over here, and then I forgot to write down my unit for that mass, which is just grams. So you might notice, it'd be nice if you notice, but it's okay if you don't. When I'm doing these calculations with my units, the grams are going to cancel out, and so are the degrees Celsius, and so my energy is going to be measured in joules. So the only thing that I really need to do here now is a little bit of calculations. So let me find my calculator really fast here. So what I'm going to plug into my calculator is that Q is going to be that 4.184 joules per gram degree Celsius times the 500 times the negative 10. Okay, so 4.184 times 500 times negative 10, and I get negative 20,920 joules. So what I've done here, the reason I have the negative is because my temperature went down. That negative means that energy is coming out. If you have a positive value for that energy, then energy is being put into your substance because it's being added to make the temperature go up. So that's an example of how to find the energy that is needed. Now, you might be very good at math, and maybe you already think you know how to find C, M, or triangle T, and those questions are actually pretty easy to do also. So if you don't want to watch from here to the end, that's okay. But if you get stuck or you find that you're having a hard time doing those kinds of problems, then you should come back for a few more examples. So I'm going to go ahead and move on to the next example here. So But I'm out of Cornell paper, so these are just going to be on plain old paper. Maybe you fit them on, maybe you didn't. It's all good. So whatever you need to do here. Okay, so if you're still watching, we're moving on to example 2. It says 50 grams of glass is given 333 joules of energy. If the specific heat of glass is 0.5 joules per gram degree Celsius, how much will the temperature rise? So I've got my Q equals Cm triangle T. That's my little map of where to put those numbers. So I'll go ahead and set that up here. And all I have to do is put things in. So let's see. 50 grams of glass, that's a mass, so I'm going to put that one right here. 50 grams is given 333 joules of energy. That means that's the Q, so I'll put my 333 joules there. And keep on reading. Of energy, if the specific heat of glass is this lovely number right there, 0.50 joules per gram degrees Celsius, how much will the temperature change? So the temperature change is what I'm looking for. How much will the temperature rise? So triangle T is what I'm looking for. So I've got my little formula thing filled out here. Oh, interesting. Okay, so if you notice, looking here, on both sides of the equation I have joules. Over here I have joules on the bottom, or I'm sorry, grams on the bottom and grams on top, and that leaves me with the degrees Celsius here. So degrees Celsius is what my answer is going to be in. And so I basically have 333 equals 0.5 times 50 times whatever triangle T is. So to get triangle T by itself, first I've got to divide by this 0.5 and this times 50. You could multiply that first or divide first. It's totally up to you. Half of 50 is 25, so what I'll end up plugging into my calculator is 333. Whoops, not with a 2 on the end. 333 divided by 25. So the answer for my triangle T is 13.32 degrees Celsius. So that's how we answer that question there. We're just finding the temperature change, 13.32 degrees Celsius. Okay, so if that's all the examples you need, then you can keep going on. So that's how we find triangle T. So next example. So our third example says silver has a specific heat capacity of 0.24 joules per gram degree Celsius. 5,550 joules of energy raises a piece of silver's temperature by 353 degrees Celsius. What is the mass of this piece of silver? So same equation, Q equals Cm triangle T. And I've got my little map here, C times M times T. And you might have noticed silver has a specific heat. That is going in the C spot, so 0.24. And then I also have 550 joules of energy. That's going to come over here. 5,550 joules of energy raises that thing's temperature. And it raises it by 353 joules, not joules, degrees Celsius. And so the question of the day is, how much mass? What is the mass? What is the mass? Okay, so M is what I'm looking for here. So I've got my 550 equals my 0.24 times the mass times the 353. I get the M by itself. I got to divide all this other junk away. 0.24 times 353. On both sides, 0.24 times 353, and so I end up with, let's see, calculator, let's see, I'm going to do the 0.24 times the 353 first, and I got 84.72, so now I'll do 5550 divided by 84.72, and I get 65, so my M is left over here, and I get 65.72 50991501414643. I will be rounding to 2 decimal places, and so I have 565 here. I'll write it here, 65.509, and a whole bunch of other numbers. If I cut it off here, that 9 says go up to a 1. Now let's think a little bit about the units. This was joules. This was joules per gram degrees Celsius. That I don't know. This was degrees Celsius, and so if you see the joules cancel out, the degrees Celsius cancels out, and I end up with grams left over. So grams is the answer on my unit. One more example after this one. All right, this is the last example. It's example 4. The question says a 15-gram sample given 204.75 joules of energy goes from 25 degrees Celsius to 60 degrees Celsius. What is the sample? And you can see over there there's a chart with the element and the specific heat in joules per gram degrees Celsius. So this question is really asking what is the specific heat, and once we find the specific heat we can use that to identify which substance it is. So we'll start with our lovely equation, Q equals CM triangle T. I'll use it as my map. There's that and the M and the triangle T, and then we'll read the equation. The question. 15 grams sample. 15 grams is my mass, so that goes right here. Then I have, it's given 204.75 joules of energy. Even tells you right there, that's the Q, 204.75 joules of energy. And that is, oops, I already used that color, goes from 25 to 60 degrees Celsius. I have to be careful there because I'm not going to use the 25 or the 60. I need to know what the change was. It will be in degrees Celsius, but to get from 25 to 60, hopefully you can figure that one out. It is 35 degrees Celsius. Go up 5 and then another 30 to get to 60 from 25. So this C is what I'm looking for. Let me pick a different color to write that one, and we'll just go with this one. Okay. All right, so C is what I'm looking for. So I have 204.75 equals C times 15 times 35. So to get C by itself, I'm going to divide by the 15 and the 35. So I'm going to plug into my calculator. I'm going to do the 15 times the 35 first. 15 times 35, I get 525, so I'll be doing 204.75 divided by 525. And I get, for the specific heat, 0.39. I've got joules and grams and degrees Celsius, and since I'm dividing these two guys over, they'll be underneath, so I'll have joules per gram degrees Celsius, which is convenient because that was the unit of the specific heat. So 0.39, I got to take a look at my chart over here. 0.39 is closest to this one right here, so my sample must be copper. It's actually pretty cool that you can be able to do those things. So make sure if you have any questions about how to do any of these problems that you are talking to your teacher. They're a wonderful source of information, and that's about it. Thanks for watching.